And where we left off was approximately here. We talked about power rule and proved it more or less, kind of an informal proof for integer values, or whole number values rather, of the exponent n. We talked about constant functions, constant multiples of functions. And these are, if you can see, these are two different sorts of rules. So the two at the top are a specific function type. If f of x is a power function, here's how I find its derivative. If f of x is a constant function, one-valued function, that its derivative is 0. The other two here are about how things are combined together. If I have a function that I know and it's multiplied by a constant, or has an extra coefficient that I'm not used to, I can find its derivative. It's just a constant multiple of what it would be otherwise. So this isn't mentioning a particular rate of change function for this g of x here. It could be any sort of function. If I have any sort of function that I know how to find a derivative of with a constant multiple attached to it, I just attach that same constant multiple to the rate of change for the function that I had, for the rate of change for g of x in this case. So the other thing we talked about, if you have sums and this extends to or differences, or even more than two terms added or subtracted together, you can just essentially define the rate of change. Each one of those you can separate out in that f of x plus h minus f of x over h sort of rearrangement, so that the rate of change of a sum or a difference of as many terms as you want is just the sum or difference of those individual rates of change. So term by term, you can find derivatives or rate of change functions from things, as long as we know how to find the derivatives of the individual pieces, which we haven't talked about a whole lot of different sorts of individual pieces so far, just power functions and constants. But power functions can hide in a lot of ways, like we talked about. They can look like square roots, or it could look like a fraction with a x in the denominator raised to a power. That's actually still something as a power function. There's a variety of things you can, a variety of different looking things you can rewrite into power functions. But let's take a look at a square root function, which we said is a 1/2 power of x. But let's talk about this from scratch, the old-fashioned way, using our trusty definition to find the rate of change of a function, f of x plus h minus f of x all over h. Because the pattern that we looked at yesterday, or Wednesday rather, with power functions wasn't about half powers. It was just using whole number powers and how you can use binomial expansion, which if I have x to the 1/2 power and x plus h to the 1/2 power, there's not a way I can multiply that out and collect like terms. So let's take a look at how I could maybe rewrite this kind of open form expression so that it's more usable. Because in this form, if I imagine h essentially 0, I've got this indeterminate form that's essentially 0 on both the top and the bottom of a fraction. That doesn't help me identify a pattern discernible in terms of x's. I could find specific numerical values for specific x's, but let's work on some algebra to simplify this. So when we're dealing with polynomials, the way that we were able to do something with this was expand and then collect like terms, add or subtract x squareds with other x squared, and then we could factor out some h's. There's no things to factor or expand here. When we dealt with that 1 over x plus 2, I believe it was, a fractional expression, a rational function, we made common denominators so that we could do something with that numerator and combine the terms, and then eventually, because of how it ended up, be able to reduce out a factor of h that way. There's another technique that you probably used in algebra that's not usually in the numerator, but when we have radical expressions, one thing that you can do with radical expressions is change them so that they're no longer radical if they're in a fraction. Usually this was in the scope of rationalize the denominator. It's something you learned in an algebra class. Like instead of writing 1 over the square root of 2, you multiplied that radical by itself and ended up with root 2 over 2. We can do that to the numerator also. Any sort of fraction tricks like that, multiply the top and bottom by the same thing, perfectly legal to do. There's a few things that end up being helpful in terms of simplification. And although that seems like a strange thing to do, like why would I want an irrational denominator? If it changes what the numerator looks like in a way that it makes me be able to combine it, then that's a useful tactic anyway. So the point of this class isn't really about the algebra, but I wanted to point out that in proving a lot of calculus, there's special algebra tricks that are incorporated here and there, and we'll do another one later, just weird tricks of algebra that help simplify or rewrite an expression in a form that's more to our liking. So the trick that's going to help us here from Algebra 2, when you have the two-term radical expressions, which were the messier ones, you had to multiply by the radical conjugate. Or if you did this maybe with complex numbers also, like 5 plus I, if multiplied by 5 minus I, within a fraction, do that to the top and bottom, the i's disappear. So with this, if I multiply a subtraction of two radical quantities here by their conjugate, the addition of the same two quantities, when I do the multiplication, difference of squares pattern, I'm going to get the first part squared minus the second part squared, which if I end up squaring these radical expressions then, like this pattern here, multiplying this fraction that we had by, same thing top and bottom. So this looks like a mess right now, but multiplying by a form of 1, assuming that this is within the domain of square root functions, and then the numerators here, the denominator becomes a mess, but the numerator follows this difference of squares pattern. So our numerator, a minus b times a plus b, gives us a squared, so I'm going to have x plus h quantity squared, square root of x plus h times itself squared, which gives us back x plus h, assuming x was positive in the first place, and h we're assuming is positive, but essentially 0, so we're not running into any weird needing absolute values situations. And same with the second half. So I end up with an ugly denominator, but a numerator, if you can see, that just turns out to be h. Now this denominator was h times this sum here, and we could expand that, but let's not, because if we don't, we have this h multiplied by this two-term expression, and in the numerator, it simplifies to just h, which means the whole fraction can be simplified to 1 over the square root of x plus h plus the square root of x, which looks kind of similar to the original expression, but because of the location, now it's a plus, and there's no factor of h as the denominator. If I imagine in this expression, I can cancel out this h over h, that's a 1, factor out and reduce, gone. I've just got this expression left. And with that 1 over x plus h, or 1 over square root of x plus h plus square root of x, if h is essentially 0, this whole expression becomes essentially 1 over square root of x plus square root of x, which is 1 over 2 times the square root of x. So it says if we imagine h essentially 0, we can simplify, let me clear this off. There you go. Simplify our rate of change function to that. So this is something that if you've looked carefully at your list of rate of change function rules that you got in recitation, this is listed separately on there. Square root of x is just a x to the 1/2. It is just a specific power function, but it's one that shows up a lot. The function square root is very commonly seen in lots of applications. So if you're dealing with needing to find rate of change functions, if you know quickly off the top of your head what the rate of change for a square root of something looks like, then that can save you a bit of convert it into power function form and use that, or going through this method again from scratch. The point of this isn't that I want you to do all of your rate of change functions from scratch using the x plus h, but for you to understand that that process will get us the magical short results that you see on tables and lists, whether it's one you got in class or one you find on the internet. But using the 1/2 power, we talked about this at the end of Wednesday. If I rewrite square root of x as a 1/2 power, and I use that power rule, which we didn't specifically talk about in terms of non-whole number powers, we'd get 1/2 times x to the negative 1/2, which if you want to rewrite that in other forms, that could be 1 over 2 times x to the half, or 1 over 2 times the square root of x. By the way, in terms of mastery test things, and again, your mastery test is going to be, let's see, slightly less than 2 weeks from now. Wednesday, October 31st, Halloween. So your mastery test is one part in class and then another part in recitation, whether that's the Wednesday, Friday, or Monday following that, but the lecture part will be first. you're not going to be asked to simplify things. So just write them in whatever form they come out. If you saw something like square root of x, you could write it like this because you memorized it, or you could write it, you could think about power rule and do something like that, but you don't have to put it in a particular neat form. And in fact, some of the expressions, and we'll go through a lot of examples of these in class on a daily basis, it's just a lot easier to look at and for us to understand if you have all the pieces in there, if you don't insert a lot of algebra. Although that's kind of a non-common thing in math class, please don't simplify your answer. It's kind of easier to see, and plus, we really don't want to grade you on whether you make algebra mistakes or not. We'd rather just grade you on whether you know how the calculus rules work, so leave as much algebra out of it as possible, and just focus on apply the calculus rules that we talk about, and then leave it at that. We'll see if you know all the derivatives without forgetting exponent rules or doing something weird wrong. Don't want that to be a part of it, nor do I want you spending time on the simplifying, because the main goal of these is they're typically rate of change functions, something that we can use to answer some questions. So creating this function is usually the middle step of some other process that we're going to be using. So in any case, square root of x, we talked about this one without the proof on Wednesday, just using power rule, but we can come up with this without using power rule, just using algebra and some tricks of algebra in order to get that. So another sort of function that we're going to talk about a lot, we're going to talk about exponential and logarithmic functions, trig functions, etc. We're not going to prove all of them in class, but just let's talk about GC a little bit, how you can either check your own work, and I know we talked about this a little bit, how you can check your own work, or check to see if you have a derivative rule correct. You can also use things like for checking derivatives in terms of, did I do this right? Those sorts of things are just, they're basic calculations. You can check them on Wolfram Alpha, the Tutor Center. Anybody there can help with derivatives because they've all taken calculus enough to know the derivatives. Or you can do it yourself on GC if you want to play around with GC. It helps remind you maybe of this theory behind where it comes from also. But to check graphically with GC that we've done this right, we might want to, let's see, where's my GC? Here we go. So just as a quick example of this, if I define the function that I want, f of x is, let's see, square root of x. Let's see, math, it's not giving me a root sign. So if here's my function and I want to explain its derivative, I'm just going to use r without any fancy subscripts to save some typing. But my rate of change function, Control 9, there we go, should be f of x plus h minus f of x all over h. And then we're going to imagine h essentially 0. What I'm going to do is just pick a small value for h. So you have to tell it what h is. If you're using that left function, you have to tell GC what left is. It doesn't know these things off the top of its head. But let's see. There we go. So if I say h is a very small number, or you could be fancy, make a slider, etc. But if I just want to graph f of x, its trusty rate function here that I know is going to be, well, approximately right. Let's see, I want to graph y equals f of x, and I want to graph, and I don't want it to be in green because I won't be able to see that. Y equals f of x, I'll make that black. I want to do y equals r of x, and we'll make that purple. And we'll see what those look like. Now, f of x is supposed to be more, the reason I'm going to put these up here together is for a different purpose. So the black function is my square root function. It's growing quickly at first, and then it grows more and more slowly, but it's growing all along. The purple is supposed to be its rate of change function. This is using trusty version, h is small, and I have an extremely large positive rate at first, but it drops quickly, so that by x equals 1, my rate seems to be around 1/2, and it goes onward from there. Now, what I really want to look at is how does this r of x graph compare with what I got for the derivative of square root of x using power rule, or as my result from doing all that algebra. So did I mess up the algebra, or did I do it right? So if I graph what I know is supposed to be at least a very good approximation of this, and I could put in some more zeros if I wanted. Notice it doesn't change the shape a lot. But if I graph y equals let's see, we had 1 over 2 times the square root of x, or you could write that in lots of other forms if you're not sure of your algebra on that part. And let's see. And let me make this one blue. So I should have a purple exact rate of change function, and the blue one I'm hoping is an exact rate of change function. And as you can see, one's right on top of the other. So despite the fact that this exact rate using our trusted form isn't quite exact, it's very close. You can see that these two graphs are right on top of one another. If I make h less small, there. Now you can see that there's a little bit of difference between them. But if you want to check to see whether the short closed form that you came up with seems to be rate, you can graph that closed form along with the definition form, the f of x plus h minus f of x over small h, and either define a small h or do a slider for h and scroll it around to see. And you can see whether they lie on top of one another. If they do, then you've got the right function. You can be sure of that, or if you were wrong, it's maybe just because you typed something wrong. But in any case, another thing that this can help us with is just kind of understanding that this seems reasonable. So exponential functions, proving their derivatives their derivative shortcut rule is a bit hard, but here's what I'm going to tell you. The derivative rule for a function in exponential form, y equals b to the x, where b is going to be a standard base to an exponential function, something larger than 0, and we wouldn't use it as 1 because that would be boring. That would be a constant function. But works out the same even if b is 1. So if b is something greater than 0, so that this function is continuous for real valued x's, because if b were something negative, like -3 raised to a power, every time I hit a fractional power like square root or something, it'd be undefined. So it'd be undefined at infinitely many values if we're looking at just real values. So we'll use b as greater than or equal to or greater than 0. The rate of change of function b to the x is b to the x times a constant. And how it turns out is that that constant is the natural log base e, of that base number b. So specific examples of this, and then we'll look at a GC graph. Specific examples of this would be if I have f of x equals 3 to the x. Well, 3 to the x, according to this rule, its derivative, which we can use this rate of change notation here. I could call this r sub f. Oh, that says r sub b of x. I thought it said r sub b. R sub f of x, or I could call this f prime of x, or I could call this the derivative with respect to x of f of x using this notation. All of these, again, mean the same thing. They mean an exact rate of change function. We're going to use the exact version of the r notation. According to this rule over here, the result is 3 to the x times the natural log of 3. So it's just a constant off. Not natural log of x, natural log of 3. It's just a constant off from being exactly its self, like how it started. But again, these functions mean two different things. So 3 to the x, if I'm looking at, that's a map of x values, independent values, to y values, output values or whatever. And the rate of change of that is a multiple of that, meaning if I were to look at a graph of 3 to the x, at every point on the graph, the steepness of it, visually speaking, the slope of tangent lines, or the slope of lines that are through 2 points extremely close, that rate of change of y to x in the area of any particular x value is going to be, the rate of change is going to be essentially the same as the y value multiplied by natural log of 3, which I believe is like 1.2. I don't remember off the top of my head. Slightly more than 1. Natural log of e comes out to be 1. If you remember, e is that number that's about 2.718. It's a nice irrational number. Euler's number. Natural log of x, by the way, remember, means log base e of x. And the natural log of a number, when we evaluate that, if I were to say something like natural log of 3 is about 1.2, I think that's right, approximately 1.2, just making up a number. This means that e to the 1.2 is approximately 3. This is something you might have talked about in recitation, remembering what logarithms are doing. They're explaining the exponent it takes to get from the base to what you see as the input to a log function. So natural log is logarithm base e. It has its own notation where we don't write the e, but log base e and ln, I believe it's from French, hence the backwards letter ordering, log naturel or something, is log base e is natural log. That's what this stands for. So in any case, thinking about graphs, let's take a look at GC for a moment. I'm going to clear this off and go back to GC. I don't need that. Let's start fresh. So if I look at y equal, I'm just going to type a function here, y equals 3 to the x power. I know that this graph is flat on the left, has a horizontal asymptote, that's the x-axis. The more negative x becomes, the closer this becomes to 0. It's a fraction 1 over 3 to larger and larger powers. So if I look to the right, it grows quickly because as x increases, I've got x. 3 to the second power is already 9, which is off this graph, 3 cubed, 27, and so forth. So if I look at what we just said was supposed to be the rate of change function, we said it was y equals 3 to the x times the natural log of 3. This natural log of 3 makes these two different by just a little bit. So one's just a constant multiple of the other. This is a number, 3 to the x times about 1.2. These two graphs being the same isn't magic. What it's saying is that the steepness of the purple graph is represented by the y values in the red graph. It just happens that they are approximately the same. They're off by a factor of 1.2. Now, if I were looking at e to the x, the natural log of e, by the way, is 1. These two expressions are exactly the same. Natural log of e is exactly equal to 1. All that means is if I graph e to the x, if I know a y value of the function e to the x, that's also the rate of change at any point on the graph e to the x. If I look at x values in any moment, the rate of change in that same moment is equivalent to the y values in that moment. So if I'm at a y value of 1, like I would be at 0, the rate of change in this moment here, when x equals 0, this is e to the 0 or 1 as the y value, the rate of change is also 1. dy dx, or the ratio of changes in this moment around x equals 0, is equal to 1. If I was looking at a value near x equal to e, so that, or not x equal to e, x equal to 1, so I have a y value of e, approximately, let's see if I can get up here. Here we go. So, let me grab my draw on this. In this moment here, x is 1, so the y value on the curve is e to the first, otherwise known as e, or about 2.7. The steepness, the rate of change of y with respect to x, is also about 2.7 in that location, meaning that if I increase the x by a little bit, the y value will increase by about 2.7 times as much. But again, the rate of change function and the actual function graphed on the same axes is usually a little bit strange because the y values mean different things. So if I had units, this wouldn't be appropriate to graph them on the same axes, because if my y equals e to the x were representing height, then my y value would be something about like meters or feet, and the y values of the rate of change would be maybe like feet per second or meters per second. So typically we don't graph these on the same axes. The only reason I did this time is because exponential functions are weird in that their derivatives look just about like their original forms. The rate of change of exponential functions is a multiple of, sometimes that multiple is 1, of their original version. So the y values and the rate of change at those y values are off by just a constant factor, and the constant factor depends on the base of the exponential function. So get rid of this. Let's go back to looking at stuff. All right, so if b the base of this function is the number e, about 2.718, then that natural log of e, since natural log is log base e of e is 1. This function can be written more succinctly. If I have e to the x, we just say the derivative is e to the x. The derivative rule, rather, I should say. If I have b to the x for any b, I can write it as b to the x times the natural log of b, whatever that number is. But it is a natural log of a number. It isn't a natural log of x. But the rate of change of e to the x is itself, strangely enough. The units would be different between the original and the derivative, but the function rule looks the same. So, we'll talk about that later anyway. But let's let's take a look at this, because this expression here is actually composed of a bunch of things that we already have talked about how to find the derivatives for. And there's a bunch of things that are connected by addition or subtraction, and there's a constant multiple in there. So even the extras beyond just pluses and minuses are things that we've talked about how to find the derivatives for. So take a minute or two, see if you can figure out how would I write the exact rate of change function, the closed form derivative function for this function p of x. I'll call it r sub p of x to use our nice notation. You could call it p prime of x, dp of x, dx, lots of things. So when you're looking at longer functions like this, make sure you look carefully, understand the structure of this. But if you can see, I've got 1, 2, 3, 4, 5, 6 terms to this function, 6 items that are added or subtracted. Each one is individually could have been its own function, but a bunch of things added and subtracted. We can take derivatives of find rate of change functions for those fairly simply, just one at a time. Some of these pieces are easier than others. Like this first one looks like a mess. But I've just got a constant multiple of some things in parentheses. And well, what's in those parentheses? 2 more terms. But constant multiples I know how to deal with. If I can find the derivative of the rate of change for what's inside the parentheses, according to our constant multiple rule, I can just tack that 4 back on. I don't have to distribute. I can just leave it as 4 times something. So I'm going to write this up here to give myself some more space. But rate of change for this, whatever notation you want to use. What is the derivative of 8 to the x power? 8 to the x times natural log of 8, right? So this is our exponential function rule. Natural log of 8. And then derivative of x to the negative 8th power. That uses power rule. So I can write plus because I see this plus there. If you're kind of just jumping ahead a step in your mind, you might just write a minus automatically. But if I, doesn't matter either way. If I want to find a derivative of x to the negative 8th power, my power rule says that the derivative should have a new coefficient and an exponent that's 1 smaller than it used to be. What's the new coefficient? Yeah, negative 8. What used to be the old exponent. There wasn't any other coefficient constant multiple on this, so just negative 8 and then x to the negative 7 or 9? 9, yeah, 1 lower. So we had 4 times 2 terms. Now we have 4 times the derivative of those 2 terms. That's how constant multiples work. Constant multiple of 4, I can just tack that back on, so I could leave it as is. Now, this next term is so short, it might also be confusing. but I'm looking for what's the rate of change of x? 1. Yeah, remember, you can use power rule in this. This is 1x to the first. So you could bring down the 1 and then reduce the power by 1. Or if you just had the function y equals x and I ask you what's the slope of that function or what's the rate of change of that, oh, that's a slope of 1. Linear functions, we often refer to that in earlier versions of math as just always slope. We can refer to it other ways as well, but regardless, the derivative or the rate of change of this part of p of x is 1, positive 1. So then we've got minus 2e to the x. So that's I've got an e to the x, which we were just talking about, but there's a minus 2 in front of it. That's another constant multiple. So I just need negative 2 times, what's the derivative of e to the x? E to the x. Nicest function ever. Maybe. I don't know, the derivative of 1 is pretty simple. Let's see. So we're on to x to the 10.7 power. Is that an exponential function or a power function, by the way? Yeah, it's a power function. Power functions have an x or a variable raised to a numerical power, and their power decreases by 1. So it becomes 1 smaller in number as the exponent. Exponential functions have the exponent as the variable, e to the x, 3 to the x, 2 to the x, those sorts of things. And we'll talk about other sorts of more complex exponents next week. But yeah, if your number is the base with the variable is in the exponent position, that's exponential function. If you have things like x squared, x cubed, polynomial sorts of things, or other powers of x that aren't whole numbers, those all use power rule. There are power functions. And so it's the same rule that we used back with x to the negative 8th power. We have a new coefficient, 10.7, x to the 9.7. All right, then we've got, let's see, minus square root of x. So you can think that of the negative 1 coefficient or just, oh, it's addition or subtraction. So I'll just subtract now. You could get the derivative to this term 2 ways. We talked about, well, either remember how it works for square root functions, memorize that as its own separate rule because it does pop up a lot, or you could think of this as x to the half, and we need to take its derivative using power rule. Either way, what is this just in, if I write a final answer in fraction radical form, what is the derivative of square root of x? Yeah, 1 over 2 square root of x. So just as a kind of memorized outcome of that one particular example, square root. By the way, if you had cube root or fifth root, it's not just 1 over 2 times something. It's related, but it wouldn't be a 1/2 that we end up with as a coefficient from those using power rule. You can take the derivative of other radicals, other numbered radicals, cube roots, 17th roots, whatever, by writing into power function form and then using that. And you'll see kind of what the pattern is, but it's not quite as simple as square roots are. What about this last term? 0, yeah, e squared, like, oh, this looks like exponential function, so shouldn't it just be itself? Why isn't e squared its own derivative? It's a constant. Yeah, notice there's no x in that. E to the second power is just a number. It's like 8 point something. So, and constant functions have a derivative of 0. So I could write minus 0, or I could just stop writing. But there's not really a lot of simplifying that I could do with this, even if I wanted to. So this would be a nice final answer. Sort of look for, find the exact rate of change function for this p of x. Any questions on any of those? Again, we use our sum and difference, constant multiples, and a bunch of individual rules. Yeah. Mm-hmm. Yeah, you could also distribute the 4. So if you distributed this 4, it'd have 4 times 8 to the x, whose derivative would then be 4 times 8 to the x natural log of 8, and 4 times x to the negative 8th, which should give us 4 times negative 8, or negative 32, times x to the negative 9. Just be careful, an algebra thing that I don't know if you're guilty of this, but sometimes it's just being in a hurry. Realize that 4 times 8 to the x is not the same as 32 to the x, for instance, right? Because this has 8 to the x power, and this is 4 to the first power. I can't combine those into, like, this isn't 4 to the x power, so I can't combine those. So if you are distributing, make sure you don't do any bad algebra in your simplification. All right, so overall, make sure you look at things to see if, like, it's very easy to quickly look at something and misjudge what you saw. Like, oh, it looks like there's a whole bunch of things multiplied. No, it's just a coefficient multiplied onto one thing. But again, we've got one other rule to add to the list that I had at the beginning, but we've got three types of functions here: power functions, constant functions, exponential functions, that we've specifically talked about and, well, not quite proved the exponential functions, but just kind of seen that it seems reasonable. What we need to talk about more, instead of just the individual function types, what I want to talk about more is other ways you can combine function types. So far we've talked about taking a function that's known and multiplying it by a constant, a coefficient, or taking a couple of functions, two or more, and adding or subtracting them. So what we need to talk about is, what if I multiply functions together? And not that I can't, but maybe I don't want to do the multiplication. So there are some other function types. These bottom three, we'll kind of use those as examples as we go along. They are listed on your sheet. I don't think we're not going to prove all of them. The inverse trig and the logarithmic functions, those involve to prove their derivative functions involves a type of derivatives that we haven't covered yet, isn't on your mastery test. Trig functions, we'll talk about a couple of them. But make sure that you know these derivative rules, even though we're not proving them all in class. But in terms of these, we've talked about constant multiples and sums and differences. I want to talk about, before we leave today, two things: products and quotients. And on Monday, we'll talk about compositions of functions. Usually, you talk about these kind of all the same day in an algebra class, how to just write the functions. But what we're going to do is find their rates of change. So if I have a product of functions, I'm going to do this like we did the sum and difference. Starting from scratch, if I have f of x and g of x and they're multiplied together, maybe it's a square root of x times e to the x. There's nothing that I can do to do the multiplication. Just like if there's addition and subtraction. If you don't have like terms, you can't do that process. You have to know how to find the rate of change without having done the arithmetic. So if I have f of x and g of x that are multiplied, whether or not I can do the multiplication, if I wanted to think about this rate of change function, just this, whatever, I'm just not giving it a third letter as a name, but f times g, I'll call that the name of it, is f of x times g of x. So I need to have, with the x plus h version in there, I'd have the f of x plus h, g of x plus h, minus the original f of x, g of x, all over h. So there's not a whole lot I can do with that. I certainly can't subtract those. In general, I can't factor out anything because I don't know what functions f and g are. But here's the other algebra trick. I said we're going to learn another weird algebra trick of proving things. What I want to do is I'm going to look at this. I'm going to add and subtract the same term into this fraction. I'm going to add in a term and also subtract it out, which should make it look the same by the time we're done. Or it should have the same value but look differently, I guess. So these ones in red, just kind of inserting those two into the numerator. I'm subtracting f of x times g of x plus h and adding back in f of x times g of x plus h. So whatever those might be in any particular function's example, I'd be adding and subtracting the same term, so this should be equivalent to the row before it, which seems like a silly thing to do, but it's actually helpful. It helps us factor. Because if you look at the line above, the next to last line here, there's no common factors in any of that, so no way that I can recombine this in any way. But in the new version with 4 terms, I can group this factor by grouping. The first 2 terms have something in common. The last 2 terms also have a different thing in common. And so I can write this as multiplied expressions, where from the first 2 terms here, if I look at those two, they both have a g of x plus h. And if I factor out g of x plus h from those first 2 terms, I'm going to have f of x plus h minus f of x left. And that's starting to sound good. If I look at the second 2 terms, if I think about factoring something out from this group in the numerator, they both have f of x in common, or they have f of x in common. What's not in common is g of x plus h minus, it would be g of x. That sounds really good, because those sorts of expressions in numerators over h are things that we've seen before. So doing that factoring, I have a fraction with a big messy numerator, but it has two main groups of terms. So hold on for a second, let me draw this in here. I've got one numerator that has f of x plus h minus f of x, and the other term in the numerator, g of x plus h minus g of x. So I can write those into two different fractions. The way we add and subtract fractions, you need the same denominator, and then you just add or subtract the numerators. I can separate them back out, undo an addition, and if I do that, now I've written this g of x plus h off to the side instead of in the numerator with that, but you can probably see why that's helpful. Is this still on? Okay. So I've got g of x plus h times this expression, which that looks familiar, and this, what used to be the second half of the numerator, now is the second term here. I've got f of x multiplied like over 1, multiplied by g of x plus h minus g of x, all over h. So this piece here, that looks like the rate of change of function f, and this is the rate of change of function g. So all I've got to do is imagine h becoming essentially 0 for those two to be true. This term's also going to be affected by that, letting h become essentially 0. But it just, if h is essentially 0, that first piece, that first factor in brackets, turns into g of x. So I've got overall, let me do it, yeah, g of x times the rate of change of function f, g of x times f prime of x, plus f of x times the rate of change of g. So there's a lot of different ways that we can write this using all the different notations for derivative, but what we have here overall is that to find the derivative of a product f and g, we end up with two products added. One half of the product is, here we go, one half of the product has one factor's derivative, the other half of the product has the other factor's derivative. So it's not just as simple as I have two things multiplied together, I take their derivatives and then multiply them together again. It's not quite as simple as with addition and subtraction because of how multiplication works. And we just proved that it was not that simple as just smack the pieces back together in derivative form. We have to do a bit of mix and match, like multiply and add. It's a bit of a process, but once you've done it a few times, it comes very quickly. We've got, oops, let me click down here. The rate of change of a product of functions is, in words, first times the rate of change of the second plus the second times the rate of change of the first. So it's two terms, again, each product in that sum has one derivative of an original factor and one original factor from the original function. So as an example, if I have f of x is 2x to the fourth minus 3 times 3x squared plus 7, in this case, I could multiply these out very easily. But I can also find the derivative of this product without multiplying them out, just as an example, and you can double check this way. But if I think here's one part, here's another part. If I'm thinking of this as a product, I know that the derivative of this first part, f prime of x, or not f, well, I do want to write f prime of x equals, let me call this part a and this part b. So I want a times b's derivative and b times a's derivative, or whatever you want to call them. Just, you can make notes to yourself, something like this. It's not formal, fancy notation, but just, what do I have to do? Well, a is this 2x to the fourth minus 3. B prime, what I mean by that is, what's the derivative of this? So what's the derivative of 3x squared plus 7? It's got one term. 6x. Because the derivative of 7 is 0. This is using power rule, 3 times 2x to the first. So coefficient of 3 and 2x to the first power rule gives us 6x. Derivative of 7 is 0. I could write plus 0, but I don't have to. But I do have to write the rest of product rule, which is, well, leave the second part alone. And there's multiplication and addition here. Oops, plus 7. Multiplication and addition here. So there's lots of different orders that are equivalent, but the components need to be all mixed and matched and added. So I need, let's see, the derivative of this first term yet, which, similar to the second, has a coefficient and power rule with a constant. So I should have 8x to the third power as the derivative of the first factor up here. And you can just leave it like this. Don't do the algebra and multiply this out and make your life more difficult, unless your goal is, I want to check this. If you were to distribute, multiply this all out, you'd get something with like, I don't know, x to the fifth power, I believe. Let's see, x to the fourth, x to, yeah, it'd be something with x to the fifth as the highest power. If you take the derivative of this, or if you multiply out this, you'd get x, something with x to the sixth in it. It'd be a polynomial, like, oh, the highest power is going to be x to the fifth when I'm done. You can check this by actually doing the multiplication here and finding the derivative from polynomial format versus using product rule. But before we go, I've got one thing that I need to give to you, which is we've got a take-home quiz for this weekend. It's already posted in Canvas. Let's see. There's a bunch of examples of using product rule and power rule and stuff like that on here with more general sorts of functions or comparing some results.